Hi everyone, let's talk about counting permutations in combinatorics. Let's say we have a set S with some elements, let's say A, B, C, and D. Then its three permutations are lists of three elements that are distinct from S. And I'll give you some examples. For example, we have the list A, B, C. We have A, B, D. We can also have B, C, D. But the whole point is that they're ordered. They're ordered, and you are not going to be repeating elements from the original set. No repeats. There is a version that allows for repeats, but we're not focusing on that right now. We're just looking at ways of permuting a subset of the elements of the set. So let's say in general we have S is a finite set of n elements where n is greater than or equal to 1. And k is an integer that is greater than or equal to 1 and less than or equal to n. And we want the k permutations. We want the number of k permutations of S. And I'll formally define k permutations for you. It's often not mentioned, but a k permutation is an injective function from, say, f from the set 1, 2, all the way through to k. We can denote it by k with square brackets around it, into S. And remember, it has to be injective, so we can't have different indices in the set k square brackets mapping to the same element of S. And we want to find the number of such k permutations. And just as a note, if k equals to n, then we just say permutations. Because in that case, you're using up all the elements of S. So there's no point in saying n permutation, just say permutation. So let me give you an example of how this is going to go down in terms of the visualization. Let's say k equals to 3 and n equals to 4. Then what we do is that we imagine there are lists of three elements, 1, 2, 3, and we draw a tree diagram. So the first index here, it can be, and the set, since there are n elements, we're just gonna assume that it's the set 1, 2, 3, 4. It's easiest that way. So for the first element here, it can be 1, 2, 3, or 4. So we're gonna draw a tree diagram. The tree diagram is gonna shoot out to several possibilities, 4 possibilities, which are 1, 2, 3, and 4. Okay? Now, it's true that the possibilities for the second index are also 1, 2, 3, and 4, but remember, we can't use up the same element again. So what we actually have only 3 elements left that we can use after each one of these. So let's write out what those 3 are. One, 2, 3. So in this case, we have 2, 3, 4. 1, 3, 4, 1, 2, 4, and 1, 2, 3. And again, in the third element, we can have 1, 2, 3, and 4, but we've already used up 2 of them. So after we use up 2 of them, we have only 2 possibilities left that we can map to. So let's do that. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. We're running out of space now, even though the original arrows were quite wide. So let's see what these turn out to be. So if we do 1 and then 2, the possibilities are 3 and 4. If we do 1 and then 3, then the possibilities are 2 and 4. If we do 1 and 4, the possibilities are 2 and 3. Then if we just keep going like that, then the possibilities are 3, 4, 1, 4, 1, 3, 2, 4, 1, 4, 1, 2, 2, 3, 1, 3, and 1, 2. So if we count up all the possibilities, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So we get 24 possibilities. In general, what we do, because of this kind of regularity, is that we multiply the possibilities at each step. And it's possible to rigorously define what we mean by possibility and rigorously prove this, but the idea is that we're branching out at each step. So we're branching out into 4 ways here, and 3 ways here, and 2 ways here. So formally, it's not easy to do, but the idea is 4 times 3 times 2 is equal to 24. So in general, what we get is that the formula is n permutation k is equal to n times n minus 1, and we're going to have k factors, which makes us end with n minus k minus 1, which is equal to n times n minus 1 all the way through to n minus k plus 1. And that's, if you know what factorial notation is, it's the product of the first n numbers. This is equal to n factorial divided by n minus k factorial. And that's our final formula for the number of k permutations of n objects. Thanks for watching, and I'll see you next time.